e keni të qashur në YouTube. Kështu që e filloj në gjuhën angleze prej tash. So it's my pleasure to introduce our next speaker in our series at the math department at the University of Prishtina, Arbër Selimi, who is at the moment doing his PhD studies at Lisbon, and he was a former student here, and we're very proud and very happy to have him here. He will be speaking about the higher structures on higher bundles and local connections, and we have asked Arbër to give us a talk that is first fairly introductory, and then he can develop his concepts later on, which are more advanced. If anyone has a question, please don't hesitate to raise your hand in the way that you want to do that. And so, Arbër, the floor is yours for about 50 minutes. Thank you.
Okay, thank you. Thanks for your presence, and thanks for giving me the chance to present my current research. Okay, so my presentation is about higher structures on higher bundles, and I will try to discuss a little bit about connections in general, but only in the usual level, where I don't move in the higher connections, but only in the lowest dimension, where I consider only like connections as one forms. And for this, I will try to give a reason why it's important, first of all, to study like principal bundles, and then I will give some restrictions on like the spaces that we are going to work with. Then after this part, I'll be able to start with defining like the notions of principal bundles and defining the connections. And in the third part, I will try to give like a categorical introduction on like a higher categorical introduction, and try to make sense of the higher definitions. And the last part is mostly about like my current research, which is about three bundles. Well, I will not discuss anything about three connections, because the theory is not known intuitive when you move in higher dimensions. So that's why I think having only like some ideas and some intuitions from the usual connections, it's enough. Okay, so first of all, like gauge theory.
Sorry, Arbër, can you open the window in full screen mode?
Okay, thank you. I can do it.
I think it's the first row in the window when it says visualizar, and
you think here? Okay, thank you, Isra. Is it final?
Yes, it's better, yeah.
Okay, and so in the first part, I will like gauge theory mostly describes the transformations that zero dimensional particles do along paths. For this, like if you consider like a point, you see how it changes along the path. And so this leads to the study of principal bundles with connections. And now the natural question is if it makes sense to consider, like, for example, paths moving along surfaces, or higher dimensional paths moving along higher dimension, like a one dimension higher self. And the answer is yes. And for this, we need to introduce the notion of categorical bundles and higher connections. And okay, so from this moment, I'm going to restrict under smooth settings. From now on, my restrictions are smooth manifolds and smooth maps. Like usually I have like surjective submersions, which means they are like maps that are that their differentials are surjective linear maps. And Lie groups, in this situation, I assume that they are groups which have like a smooth structure, where also like the multiplication and inverse map are continuous. And another category that I need is the category of Lie groups, together with Lie group homomorphisms. And they are defined as, they are like categories where like objects and morphisms are smooth manifolds, like the set of objects and morphisms are smooth manifolds, and the source and target maps, like whenever you choose like an arrow between two objects in gamma 0, let's say like a morphism, then you can always have like the source map is like the starting point of such a map, and T is like the target map, like the end of such a map. And under these conditions, I need also like the condition that my maps are surjective submersion. Well, the fact that they are surjective comes from the fact that they are like just, it's not needed like in the condition because it's trivially surjective, but they are submersions. And morphisms between two Lie groupoids are given by pairs of map connecting morphisms and objects and morphisms, and they are compatible with maps S and T. And well, in the moment that you want to study like paths on a space, and you try to consider some families of maps which gives you like the same transformation at some point, then you will get like the path space, and you will get some equivalence relations on it. And these spaces are infinite dimensional spaces, so you cannot really have like a smooth manifold structure, but still you can have like a notion of smoothness, which is called like, and they are called diffeological spaces, where you replace charts, open charts, with Rn spaces, and you consider only some specific families of maps. But okay, like the last part is I only wanted to mention here because in the moment that you introduce like the path space or anything that is infinite dimensional, you need to move to another notion of smoothness. And I think one of the best ones is like the notion of diffeological spaces. You can still, in many cases, you have like some other kind of smooth manifolds, like Banach manifolds, but usually we restrict in the case of diffeological spaces. Whatever they are not that important, but understanding like the notion of smooth manifolds, I think it's a good intuition like to work with diffeological spaces because they are also like special cases of diffeological spaces. Okay, and now what are like principal bundles? So my settings are base space X and a Lie group G, and principal bundles are simply generalizations of products X times G. And in general, if you consider only
Arbër, sorry, may I interrupt you just for 1 second? I'm sorry.
Yes.
So because obviously we have a very diverse audience, and we want to make sure that people have something to think about, some examples. So if you don't mind, when you mention the smooth manifold, the Lie group, could you just tell us what are the examples that we should have in mind before telling us about the principal bundles? Because obviously, you know, some people haven't seen these notions. So
yeah, well, I understand, and I know that it's like something that, like I understand, like that undergraduate students may not have seen them. But okay, so
how should we think about these?
Okay,
about an example, and that would be really instructive.
Okay, about like smooth manifolds, you can just consider like smooth manifolds are just whenever you have like a smooth map from Rn to Rm, and whenever you have like a regular value of a map, then you have a pre-image, and these pre-images have a nice property because locally they can be described as spaces that are homomorphic, that are diffeomorphic to, or let's say, let's move to another level that maybe everyone understands, assuming that everyone had like a course in metric spaces. They are homomorphic, and the homomorphisms are smooth, so that they are homomorphic locally to spaces, to Rn spaces, like to vector spaces of dimension n. So for example, let's say if you have a map from R3 to the set of real numbers, and then if your map, if for example the value 1 is a regular value, whenever you take the pre-image of that value, you will get something that locally looks like R2. And for example, if you consider the map from, again, let's go to the map of, let's consider like, again, like the maps let's consider like the norm from R3 to R. And if you consider the value 1 with a norm map, the value 1 is a regular value. And if you take the pre-image, you get the sphere. And locally, around every point of the two-dimensional sphere, the space looks like R2. So that's like one of the most basic examples. And I think in many situations, like one of the first notions of smooth manifolds is like the notion of manifolds that are embedded into Rn, like coming from maps that are surjective submersions. And okay, so if in additional, you have like a space that looks locally like Rn, and you have a group structure on it. And you know, like whenever you have a group, you have two maps. You have the product, you have like the product, which has to be smooth in that case, because you want to stay under like the same category. And additionally, whenever you have like a group, you have also like the inverse map. And also you ask that the inverse map to be smooth. And like the most basic example is the set of real numbers. And this is, you have like the additional structure, and together with the additional structure, this is a Lie group, because whenever you, like the addition is like a kind of a linear map, like you have like again some polynomials that you're adding there. So it's a smooth map. Also like taking the inverse, like from like the inverse with respect to the addition. Again, it's a smooth map, like the map f of x equal to minus x is smooth. So that's why you have like a Lie group structure in it. Other examples are the circle, where you have like, again, like the addition of angles. And in that situation, you again get like a Lie group structure in it. Do I need to give like more examples, or it's enough?
I think it's okay for the moment. Yeah, thank you so much.
Okay. Okay, now let's move to the next stage, where I'm assuming that my base space is a smooth manifold. So you can just think about something that looks like Rn and a group G that has a smooth structure. And now, whenever you consider like one of the most basic things that you do, for example, in set theory, is to consider the usual product of spaces. But in the moment that you introduce a topology, you can do something more. You can have like some twists. And in that situation, it's not necessarily that you can get like always a projection in the first coordinate and in the second coordinate. So principal bundles in general are just a generalization of product spaces, and you assume that you don't have a projection in the group G. So in that situation, you have something, this is called a principal bundle. It's not disallowed to have like a projection, but usually it's not necessarily that you can get a projection. Okay. And one of the most basic examples that maybe everyone have seen in like if you remember like the Mobius band from calculus 4, when you really do like when you consider like a surface with only one side, this is like the most trivial example, like let's say in that situation of a fiber bundle, because in this situation, maybe I have like a drawing somewhere in my computer. Let me see. Yes. Okay, so it's a space that looks like this, and it's like a surface that has only one side, and the circle is the base space. And in that situation, the fiber is like an interval. Well, in that situation, you don't really have like a principal bundle, but you have like kind of a vector bundle. So in this situation, you can project along this circle, but you cannot project in the fibers. And the easy fact, the reason why you cannot project is in the moment that, for example, if you consider like just a path along it, you will get something that is again connected. But in the moment that you have something that is a projection, and if you remove a line, then you will get two copies of cylinders, but in the case of Mobius band, you will not get, and that's the reason why you don't have a projection in the in this coordinate. And this is, I think, the most trivial example of a vector bundle. Well, okay, so from a vector bundle, you can always construct a principal bundle, but that's not a very important issue for now. But it's like a good point how you can have a good interest about principal bundles and how they are not trivial. And now I'm going to give like the formal definition. And before giving like the formal definition, you can really see that you want something. Let me go back again to the drawing here. So whenever you move here, you always want that your fiber to be preserved under some maps. So this, to be able to define it, you really need an action on your total space. And for this, I will define what is an action of a group in a set, but I will make a restriction where I will assume that my group G is a Lie group, and I will act on a smooth manifold. So in this situation, I need to ask also that the map R from X times G to X to be a smooth map, and it satisfies the following two properties. So whenever you choose a point X in the space X, and you act with an identity element, you will not change anything. And acting by G1, firstly by G1 and secondly by G2, is the same as acting simultaneously. So here we are acting by G1 first and then by G2, and here we are acting simultaneously. Okay, for our work, there are two important actions. The first one is like the free action, which kind of says that you have kind of notion of injectiveness. So whenever you have like a map, whenever you have an action R, and you ask that the value of Rxg to be X, and this is true only when G is like the identity element in the group G, then such an action is called free. And in the moment that you ask that your map to be surjective submergent, so it means that whenever you choose a point in X, you can find, so whenever you choose a point Y in X, you can find the point X in X and an element G in G, such that G times G acting on X is equal to Y. Well, okay, so in the moment that you work with smooth data, you also ask that your map to be not only surjective, but surjective submerged. Well, okay, so in additional, if you assume that both these two conditions are satisfied, you will get a situation where your space X is diffeomorphic to the group G, like it's a homomorphism. So it means that they are like the same spaces, like they are topologically the same. So you can kind of have a group structure also in the space X. And that's what happens whenever you consider like a principal bundle, like along the fibers. Fibers are always going to be diffeomorphic to the group G. Okay, now I'm able to, after I've introduced like the notion of action, I can introduce what is a principal bundle. And a principal bundle is given by the following datas. It's given by a surjective submersion P to X, where P is called like the total space and X is called the base space. And additionally, you ask that the map where you project the first coordinate into the second one, and whenever you choose like a point here and you map it here along the second coordinate map, you will get, like you do it with the right action, then this map is diffeomorphism. And well, this space is just like the pullback along like the map pi. So it's like the set of all points P1 and P2 such that pi of P1 is equal to pi of P2. So we are considering, and well, okay, so maybe it can be like a very natural question from everyone because, well, here we are just taking like a usual product of two smooth manifolds, and you can guess that, for example, if you have here an n-dimensional manifold and here an m-dimensional manifold, whenever you multiply them, you will get a space of dimension n times m. Like That's like, it's like multiplying Rn and Rm. But here, what you are doing, you're considering a subset of the product P times P. So you're considering all the points P1 and P2 such that this is satisfied. And well, it can be a natural question from you, is this really a smooth manifold? And yes, it is, because this map is a surjective submersion. In the moment that you have a surjective submersion, whenever you consider like a pullback diagram, you will get something that is a smooth manifold. Okay, now there are some other different descriptions of principal bundles. One of them is like, okay, in additional, like in many cases, you ask also that your bundle to be locally trivial, but I will not make such a restriction. But okay, you have like many different equivalent definitions, and the two most intuitive ones is, you know, like whenever you restrict to this kind of local datas, and you choose, okay, so not, first of all, not always you can choose when you have like a topological space X, an open cover that is nice enough. But in the case of smooth manifolds, you can do it. So for example, you can always choose an open cover where like along the point, they looks like Rn, and you can assume that also like the intersections are again contractible. And okay, so I'm having like all these assumptions in mind. I did not write them because they are sometimes unintuitive, but you need like a nice cover which has like some properties. But okay, here I'm going to start with an open cover, and whenever you choose like an open cover in the previous definition, what you can get whenever you consider like intersections that are non-empty, there you will get like some families of maps Gi and Gij from the intersection to the group G, and you will get a relation like about the, whenever you multiply these two maps pointwise, you will get this relation. Well, okay, I don't know if I can make a drawing here, but okay, it's like having a composition of two maps. So Gij and Gjk, and you will get like Gik. And that's like one, that's like the first definition of like, it's like an equivalent definition. Well, okay, I don't know why I made a mistake like in these numbers. And another definition, equivalent definition of principal bundles is via classifying maps. So whenever you start with a principal bundle, you can always construct a continuous map F from X to BG, and like the space BG is the classifying space of the group G, and this is this is like one of the constructions that you can associate to a group G. You have like some different ones, but the most familiar one is like the Borel construction associated to a group G, where you just consider kind of the nerve of the group G, and in that situation, and you take like the geometric realization, and that space is called like the classifying space of the group G. And here, well, okay, so what you can do, you can, whenever you start with a principal bundle, it's like a topological procedure that you can construct a map F from X to BG. But moreover, like it's not necessarily that the map F that you construct is unique, but they are unique up to homotopy. And also, if you choose a map from a specific homotopical class, you can always construct a bundle. So whenever you choose, like whenever you introduce like a notion of morphisms between bundles, and you say which ones are like the same in that category, like not only diffeomorphisms of spaces, but you need like also to preserve all the structure, you can always reconstruct one of them using that property, like using a map F. And whenever you choose two different maps, you will construct again another bundle, a principal bundle, but you can show again like that they are isomorphic principal bundles. So these are like equivalent definitions. There are many equivalent definitions of principal bundles. Okay, so here this is like a very this leads like to the notion of check cohomology. So whenever you consider like, for example, the cover U, you can just take like this kind of family of maps, and then take like all refinements of all covers, and then consider the co-limits of these sets, and you get a set. Well, also here you get a set of homotopy classes of maps, and you can again find a bijection between these two sets. Well, okay, here I'm under the assumption that my family of maps is smooth, but what you can do is like you can prove that smooth families are the same ones as the continuous ones, and in the case of continuous ones, you have a kind of a direct equivalence between this definition and the analog one for the continuous ones. Okay, now until now, like I just gave like definitions of principal bundles, and now I will add like the notions of connections. And I will start with a very let's say geometric definition, and then I will mention like an equivalent description, which is using differential forms. Okay, so again, I know that my map pi from P to X is surjective submersion, and when you consider like the differential of this map, you get a map from the tangent space of P to the tangent space of X, but point-wise, you get a linear map from here to here. And surjective, and the map P pi being a surjective submersion implies that this map is an epimorphism. So this means that the kernel, this means that this map is a surjective, and in the moment that you have like that the map, that the space pi is of a higher dimension than X, your kernel is not always trivial, but even if it's trivial, you can still like define, but then you will have something trivial, like a trivial kernel. So we can consider like the kernel of this map pi, and we call this as the vertical subspace of the tangent space. And here I have a vector space over each point. But in such a situation, whenever you consider, whenever you do such a reconstruction from surjective submersion, you will always get, whenever you consider like pointwise these kernels or some subspaces, you will get again like a bundle structure on it. So whenever you have like a map that is a surjective submersion, like a bundle structure is always preserved, like is saved. Because it's not necessarily that if you have like a pointwise vector space or a pointwise group over a point in the base space, it's not necessarily that you can glue them together to make something that really fits in a principal bundle. But in that situation, you can do it, and we can create a vertical bundle associated to this projection map. And now, what you can do, you can consider all complements of this subspace into here. And these subspaces, whenever you consider them, whenever you glue them together, which is again like possible because you can write this as a direct sum of this vector bundle and the vector bundle created by these spaces, then you get a notion of a connection. So a connection is just a smooth choice of complements HP of VP into the tangent space. And additionally, you ask that these subspaces are equivariant under the right action on the principal bundle. And such choices are called connections. Well, the next definition is like the one that is more algebraic, and whenever you work whenever you need to do some computations, you need to rewrite the definition, because okay, so this is like a very intuitive definition, but using it directly, it's not that easy whenever you try to do some computations. So you can make an association, and you can do it in the following way. So whenever you choose such a family of complements HP, you can associate a G-valued one form to this connection. And this is given by the following formula, where along H, they are given this form evaluated on these vectors is trivial, because these are like linear maps, like pointwise, they are linear maps on the tangent space. So they are given trivially on H. And for other points, like whenever you choose a point V, which does not lie in H, this is equal to X, where, so well, here it's not, it has to not be like the capital X, but it's like the same X, where V is like the solution is like equal to this value. Well, okay, so it's again like an exponential map. You can think about exponential maps of matrices, and I think that's like enough for you to understand that notion. So this is like the value of, so for these values of V, you get X. So in this way, you can create a one form. Well, okay, again, a question that you can ask is that, is this form really smooth? Yes, it is. And something else that you can additionally prove is that this form satisfies this relation. So like the right action, whenever you consider like the right action, and you consider, you can write it as this composition. Okay, well, okay, so this remark is not that important for us, but it's like just a property that comes from here. It's like just rewriting that property. So this equivariance can be rewritten in this way. Okay, now let's move to the use of this kind of, okay, so now what we are trying to do is like exactly trying to describe the move of these horizontal spaces along a path. Whenever you choose a path and you have like a starting point, you want to see how this, how this subspace moves along this path. And we have like the natural question that if we have like, again, a smooth path, if it's possible to describe the change of H along this path, and the answer is yes. And we can do it in the following way. We introduce the notion of the parallel transport. So whenever, okay, so we start with a path into the base space X, and we assume that gamma of 0 is x0 and gamma of 1 is x1. And then the connection defines a map from the fiber of px0 to the fiber of x1. And more precisely, we can define it in the following way. So the parallel transport, whenever you choose a point P0 here, the parallel transport along this path gamma is defined to be gamma tilde of T1, sorry, gamma tilde of 1. So it's a typo here, where gamma tilde is the unique path that lifts the path gamma. And moreover, it satisfies this property, that the differential of gamma along every point from 0 to 1 is an element of the horizontal subspace of the tangent space. Okay, now if you choose a path from x0 to x1 and another path from x1 to x2, you can guess that you can do 0 to x2. And that's like the notion of concatenation. So you can redefine a path where, like in the first half, you just do like the path twice quickly from x0 to x1 and do the same from x1 to x2. Okay, here again, smoothness can be a problem because whenever you glue two paths at the endpoint, like in that situation at x1, it's not necessarily that gluing them there you get something that is smooth, but there is a way that you can fix it. And the way how you fix it is by just assuming that you are considering only paths that at the starting point and that at the end point, they are trivial, they are constant. And well, why you can do it is like the most basic idea that you can do it. So whenever you have like a path, it's like just multiplying it with a bump function. And that's like something very natural that you can do. Okay, so in that situation, like, sorry. Okay, so whenever you consider the concatenation of two paths, and under the assumptions that that I mentioned above, that they have sitting instance, then you can compose them So you can compose two maps of like two parallel transport maps, like if you choose like a path gamma from x0 to x1 and another path gamma 1 from x1 to x2, then you can compose them. Well, okay. Additionally, you have that you can just consider like the reverse path, and the reverse path gives you exactly the inverse of this map. So this kind of parallel transports gives you a groupoid because you have like an inverse there. And a very intuitive question is that if we choose different paths from x0 to x1, is it possible that they define like the same map, like the same parallel transport map? Because that's like a map of two kind of groups, because px0 and px1 are groups in that situation. So for these two groups, if you consider that map, is this choice like whenever you choose different paths, is it necessarily different? And the answer is that in some situations, if you have like an additional condition for the paths, if you are able to relate the paths gamma, two paths gamma and gamma prime going from x0 to x1, they can induce the same map, parallel transport. And the condition of homotopy, which means that I think that the easiest way, I did not want to write a notion of homotopy and thin homotopy, but I will try to mention like the one of like in the dimension one of the most basic definitions. So if these two paths, gamma 1 and gamma 2, and if you try to fill the area between them, you will not have area there. So you don't have anything to fill in that surface that you create. So it's going to be again something of dimension 1. It's not that you're going to have something of dimension 2 whenever you choose two paths that gives the same parallel transport map. Well, or like another intuitive point of view is that you can see this map like when you glue like these two paths, you can create a graph. It's not like you can create a tree. It's not going to be only like it's not going to have like some loop somewhere. It's going to be a tree. And this notion is like very important also in higher dimensions. And okay, so I think the best, like some people, they just make some frictions here where they usually assume that their path gamma is just for different paths, they just assume that like they don't take like a specific equivalence relation, but they say like, let's take like the smallest equivalence relation such that this parallel transport agrees. But in the case of thin homotopies, it's possible that you will get like an equal parallel transport even for things that are not thinly homotopic. And having such a definition in higher dimension, especially in dimension 3 and higher, is not that trivial. So, but there are like some different attempts, but I will not mention them, but it's like a very important thing, like to kind of generalize that notion of thin homotopy to make sense in the most general categorical settings. Because if you make like only like the usual thin homotopy, which is kind of a rank condition on your smooth map, it's not going to be enough. Okay, so I see that I'm running out of time, so I will try to say something a little bit more quickly. And if I restrict not in any kind of path, but in loops, then, and if I take like this kind of thin homotopy equivalence relation, I get a group. And in this way, I get what you can prove that this parallel transport map is like kind of a G equivariant. You will get a map holonomy from this thin homotopy group to the group G, and this is called the holonomy homomorphism. And so what we did here, what I tried to explain here, is that I started with the group G, and whenever you do like a choice of a connection, you can always build such a holonomy. But also there is like a procedure that whenever you start with a homomorphism from the thin homotopic group to the group G, you will be able to reconstruct a principal bundle and also a connection of it. Well, I did not put the connection insights in my like the connection part, like in the algebraic setting. I did not put but only like the geometric one here. So you have seen that we did a construction from principal bundles with a connection to a holonomy functor, like holonomy homomorphism, but you can do also other way around. And this is one of the main questions in the area of gauge theory and higher gauge theory. Well, in dimension 2, the problem is solved, but in higher dimension is not fully solved. Well, even like the notions of higher bundles are not properly defined and they are not really completed. So it's like a work in progress that I'm also working on it. And now what you can do here is that you can see everything in some categorical aspect. Whenever you consider principal bundles, you can give a decent notion of morphisms between them, and then you can define a category of principal bundles, and usually you denote it in this way. And well, again, you can define also transformations, which are called gauge transformations between connections. And then this way, you have like the category of principal bundles with connections. And this category is equivalent to the category of holonomy homomorphisms. So whenever you have two homomorphisms, like a group, like groups, you can see them as categories with a single object and morphisms, the group G. You can see holonomy homomorphisms as functors between them, and you can define natural transformations. And this category is going to be the same as the category of principal bundles with connections. And naturally, you can ask if you consider a path that moves along, not only like a point particle, but a path that moves along a surface, if you can really give a similar notion. Well, in that situation, whenever you consider like the path, you're considering some additional properties, and you will add. So even if you are staying only with the assumption that you're working with a group G, the group of automorphisms of the group G, which are like the isomorphisms of the group G, it will appear like whenever you consider like the full path, like whenever you consider like a path between them, then you will have such an additional structure. And in level of connections, you need a connection for the group G, like in the group G, and also connection for the automorphism group. And in this situation, you can really relate them only in the situation where you have like some notion of only when you can kind of relate these two connections. But in the moment that you have like two structures, two spaces in your like two groups that are important in your group, you will lead to the notion of categorical groups. So it's a natural thing just to generalize that specific example. So moving from groups to 2 groups, 3 groups, and so on, like also to infinity groups. But I will try just to explain the lowest level. So I will make a jump from categories to 2 categories. Well, okay, so how a category is given by a class of objects and morphisms, and you kind of compose them. You have sometimes inverses, and you have some associativity rules. Well, not in a category, you don't have always inverses. Inverses you have only when you restrict to group weights. And in the higher level, you want kind of to have a map between 2 morphisms, 2 functions. And then you also want to compose them. But as you can see, you can compose them in 2 ways. And then if you consider like such a diagram, you can think that, okay, here we can read it like the multiplication in 2 ways, where we multiply G2 first and then G1 prime and G2 prime, or we can multiply vertical, this one, and then horizontally. And these 2 multiplications in the level of 2 categories, they are asked to be equal. And this is called the interchange law. Well, okay. Similar diagrams you can make in higher dimensions. So whenever you have a 2-cell, you can put a 3-cell between them, a 4-cell, and so on. And you, in each higher level, you have more coherence conditions. And sometimes it's not necessarily that, as in this case, for example, if you have the morphism here, it's not necessarily that they are going to be always equal, as you have, for example, only if you treat the case of categories, but you can just find a higher cell that kind of relates them. And that's why you need usually like the notion of higher categories. Okay, and now I will try to give the most basic examples of two categories. And the most basic one is the category of categories. So objects are categories. Functors between like these categories are morphisms, and two morphisms are like the natural transformations. Okay, so in the third level, you cannot really always do it, like in all higher dimensional levels. And okay, so here I also mentioned like that the category of homomorphisms is exactly kind of a point of view that you get from there, because you're considering like groups and morphisms between them, which are like, so but there, your objects are functors and your morphisms are natural transformation. And also here you have like kind of, whenever you have like a two category, you have also a category with objects morphisms and morphisms which are two morphisms and so on. Okay, and now one can also do another example where you consider, whenever you have like a two category, you can consider like the mapping space category, where your objects are functors. Two morphisms treat like only like the natural transformations, but you allow them like to be kind of weak transformations, and you call them pseudo-natural transformations. They need to satisfy some other relations, which are not that important, but you need some conditions. And two morphisms are kind of pseudo-natural transformations. And this is again a two category. And now the question is, what happens in the case of two category? And the answer is negative. You don't get a strict three category in terms of, you don't get in the when you consider like these kind of interchange laws, you don't get kind of isomorphisms between, you don't get equalities between them, but you get like only some isomorphisms between them. Like you get some higher cells that connects them. And in this situation, you lead to the notion of some weak categories that I will explain a little bit later. But okay, let me give you some other examples of higher categories. Like, okay, so the notion from groups, you can jump to two groups, where for a two group, you ask this, it's like a category where you have like a set of objects, gamma 0 and gamma 1 is also a group, but also you ask that the source and target maps to be group homomorphisms. The most natural definition that of two groups is via cross modules, and a cross module, like you can prove like an equivalence of two groups, and cross modules are given by homomorphism. This is like just a general, like it's a twist of modules or vector spaces, where you have like a homomorphism from L to N and an action of N into L. Well, in the case of vector spaces, for example, you have the action of R into your space, and they satisfy these two properties, like this conjugation relations. And okay, everyone knows that, you know, well, I can assume that you may know that whenever you have like a Lie group, whenever you consider like the tangent space over the identity, you have like an additional structure, which is a Lie algebra structure. And also in this situation, you get and you differentiate this map and this action map, and you get the notion of a differential cross module, and you can give like a abstract definition of differential cross modules. And okay, again, you can jump, you can see, for example, the two groups as two group weights, where you have a single object, morphisms are given by gamma 0 and two morphisms by gamma 1. And again, a two group weight that you have like also like the, okay, so there you have like a single object, but if you ask that you have like more than one object, and if you have like a more structure in your base space, then you get like the notion of a three group. And again, like a three groups are kind of related or equivalent with two cross modules. And a definition of a two cross module, like long definition, where again, in this level, whenever you move like one level higher, you always have like some additional maps, some additional actions, where here you have like an action on N in L and M, and you have a Pfeiffer lifting map from the product M to L, which is an equivariant, and they satisfy these properties. And okay, a natural question can be why all this discussion is important about two cross modules, and why we don't consider like only some specific situations that we get under the restrictions that we allow only like some usual notions of thin homotopies, but there you will get only two cross modules where the group L is going to be always abelian. And in that situation, you are not going to be able to model all CW complexes, like all homotopy 3 types of CW complexes. But in the case of two cross modules, they do model all of them. So that's why you kind of don't make such restrictions, because you don't want to lose like homotopy types of your spaces. And now, as I mentioned before, again, I can see this two crossed module as a kind of a version of a three groupoid, where I have a single object and morphisms given by Mn, two morphisms given by M times N, and three morphisms given by L times M times N. And in this situation, you don't get interchange law, but you need a three cell, and that's why you have like a weak notion of categories. And in the moment that you ask, I will try to finish in 2 minutes or 3. So in the moment that you ask to kind of weaken all like the equations in the one of the previous slides, then you get like a notion of weak categories. But if you don't ask in the third level, if you don't ask that everything to be weak, but only a semi-weak, then you get a notion of great categories, which is enough because they do model, like great groupoids do model all homotopy 3 types. And in a similar way, as I mentioned before, you can define a right action of 2 groups and 3 groups on a groupoid, or a 2 groupoid in the case of a 3 group, and they satisfy these equations and this commutative diagram. And like if you remember, we had like also diffeomorphism in our definition of principal bundles, but in the moment that you discuss, that you move in the level of groupoids, because your total space in this situation is not going to be a manifold, but groupoid or a 2 groupoid, you need a different notion of equivalence, which is called like the weak equivalence, and you ask that kind of to have like some injectiveness, which is again explained by this pullback diagram and astrojective submersion. But in the case of 2 groupoids, you additionally ask that you have like a weak equivalence of associated groupoids, and also astrojective submersion in level 0 as in the previous case. So finally, I will try to finish here, is that the definition of principal 3 bundles over a space X, which is with a structure group, with a structure 3 group H, and the total space P. And you ask that this to be a surjective submersion of groupoids, where here again, you consider like the groupoid with objects, morphisms, and 2 morphisms, like only XXX in each level, and a smooth right action such that this is a weak equivalence. Again, also in this level, you can add like the notions of morphisms, 2 morphisms, and 3 morphisms, and make them as a 3 category, and study these three categories and comparing them with some equivalent definitions, which is where one of them is explained here, where you follow the following, where you start with notion of principal groupoid bundles, you apply some kind of specification, get like a notion of abelian and non-abelian bundle gerbs, and then from there you generalize to the notion of 2 cross-module bundle gerbs, and then again you apply some process of Schifification, you get a 2 cross-module 2 bundle gerb, and then you can prove that these two are the same as these 3 bundles, and also in level of morphisms and two morphisms and three morphisms. And one of the last description of three bundles is via post-cycle descriptions, where in the preview, like in the first slide, we had like only one relation. But as I said before, here you don't have a strict equation, but you have like only a weak. So you need to add a two cell there. And the same also in the second dimension. Okay, you can multiply them only if there is like a target of this is equal to the source of this one. You need like to fill a tetrahedra where you multiply these two faces, and you need to fill it with a 3 cell. And in the level of 3 cells, you don't have a 4 cell. So you get a 4-dimensional tetrahedra, and the multiplication of the first 3 cells gives you the multiplication of this cell with this cell, and you can glue them together only if you have an additional factor like this. I think that's okay. So what you can do here is that you can really prove that all these definitions are equivalent. And question is that if you have like also a homotopical description, that's also something that I'm trying to do. And but that's something that I'm not done with in my work, so that's why I did not mention here. Thank you for your time. I think I forgot to put a slide to thanks everyone. So thank you for your attendance. Maybe I was a bit fast.
Thank you, Arbër. Thank you very much for this presentation. Now I will ask the participants if they have any questions for Arbër. So Hamdi says thank you. Islam, do you have any questions?
Yeah, I had one about holonomy homomorphisms, where you said that you can construct a bundle with connection from that.
Yes.
And is that construction unique? Like, does it come uniquely from the homomorphism, or you can get different ones in a sense?
Okay, so usually you get a unique isomorphism bundle. Just kind of modify the bundle a little bit, but it's still going to be isomorphic bundle. It's unique up to
thanks.
Yeah.
Okay.
Okay, thank you, Islam. Does anyone else have a question for Arbër? I don't see. So, all right. I think that's great. So with this in mind, I think
can I say something more?
To thank you, yeah. Well, as long as you're brief, because obviously we have to end this in a couple of minutes.
Yeah. Well,
thank you so much.
Okay. I just wanted to mention that this notion of holonomy can be extended in dimension 2. In dimension 3, there are attempts also in infinite dimensions when you consider like when you replace like the notion of two cross modules and two cross modules with simplicial groups, because you can recreate cross modules and two cross modules but from simplicial groups, because what cross modules and two cross modules are just simplicial groups that they're more complex is of dimension 1 or 2. So you can really think about something infinite dimensional. And another attempt is like using so what usually you do is like you define these notions of holonomy locally, and in local terms you need only like some Lie algebra structure, and in the infinite dimensional level you have like some notion of L infinity algebras that you can do these generalizations. And there is a result by Andre Henriquez that you can integrate them, and you get something that is kind of a generalization of Lie groups, which are like some Kan complexes that satisfy some specific properties. And for these Kan complexes, one can prove that they are the same as simplicial groups. So there is a hope that some results can be produced in that way. And I think one of the most difficult things is that to define a good notion of thinness that you can really put in your definition.
Okay, so thank you so much again, Arbër. Faleminderit shumë. Faleminderit, thanks everyone. Faleminderit gjithëve. Faleminderit shumë. Edhe shihemi pas një jave, sepse pas një jave është prezantimi I Toni Shaskës, për cilin do ta merrni emailin së shpejti.
Apo në pak këtë profesor, a je I lirë në njërin prej këtyre dy ditë me qenë në Kosovë?
Shkëmbemi
Ose
me
shkurt.
emaila. Po, po.
Okej.
Faleminderit.
Okej.
Faleminderit shumë.
Faleminderit Arbër Qendrim për
Okej.
organizim.
Faleminderit.
Mirë.
Gjithëve.
Faleminderit.
Faleminderit. Faleminderit Bujar, Kajtaz, Menderes, e të tjerë, Edver dhe student. Mirupafshim.
Tonë.
Tum.